Okay, hello all. We are starting video 2, section 4.1. Let's get started. I don't like to waste time. All right, so here in example 4, we have to find the critical numbers of f, the intervals on which f is increasing and decreasing for the function f of x equals 1 over x. So again, what I always like to do is first write out our domain of f. Okay, so what's our domain of f? Good, all rails except for 0. Okay, I heard someone say it in the video. All rails except for 0. Okay, so what that means is this. If, when we do f prime, if one of our partition numbers happens to be 0, then it cannot be a critical number because it's not in the domain of f. And that's all that means. That's the big difference between recognizing whether your partition number is also a critical number. Okay, so I'm going to rewrite f of x as as x to the negative 1. All right, we know we have to find the derivative. And so that's negative x to the negative 2. And so negative 1 over x squared. What's the domain of this? Or you can just go straight to the partition numbers of this. So I could just say, well, what's the partition numbers? And so that would tell you, okay, I need to look for those values that make the function that makes f prime 0 or discontinuous. And again, since there's a constant whenever you have a fraction, if there's a constant in the numerator, you can't have a 0. Okay. And you can set your function equal to 0 to show that it'll cancel off. So you can solve for it if you want, if you're not convinced. But yeah, we have that constant there. But we have a bad point, right, at 0. And so now the question is, well, is 0 a critical number? And you go back and look at your domain of f, and it's not, right? Because in order for it to be a critical number, it has to be in the domain of f. So this is not a critical number, but it is a partition number. And so we're going to use that for our sign chart. All right, so sign chart. And let me just say something. I don't think I stated it clearly in the video, but remember that f prime being positive or negative, and it's telling you what's happening in terms of increasing and decreasing to your function f. Okay, and so let's look at this. So f prime of x is negative 1 over x squared, right? And so we have 0 as our partition number, and so we can use a test number of negative 1 and 1. Okay, and I'm not going to put it in the table. You can just and I really just want to know if the outcome is going to be positive or negative. And as you can see, x squared would always give me a positive output. And since in the numerator we have a negative 1, then both these will be negative. So that means the function of f is decreasing. And you should remember the graph of this function. This is one of our parent functions. So I don't even need to pull up a decimals for this, right? Because you should remember that it looks like that. And we have actually a vertical asymptote at x equals 0. Okay. So notice the difference in the last example 3, we had a vertical tangent. Here we're having a vertical asymptote. And notice why that might be, right? Well, if you remember in the example 3, that value was a critical number, and here it's not a critical number. All right. So if you're thinking that might have a connection, then you are on the right track. Okay, let's move on to another example. All right, so let's spice it up a little bit and add in a log. Why not? Okay. So f of x equals 5 ln of x minus x. So find the critical values of f and intervals where f is increasing and or decreasing. So here, let's talk about the domain of f. And what you should remember is this. First of all, when we're talking about domains, remember our 3 restrictions, right? Denominators, even roots, and log functions. So if there are other terms that don't have a denominator, don't have an even root, don't have a log function, then we can ignore that when we're talking about domains. So that x right there, we can ignore that because that's not giving us any additional information about our domain. But we do have a log function. And you should remember the domain for log functions are all positive numbers, right? Or whatever makes your input inside your function positive. Since it's just x, the domain is all values of x greater than 0. Okay, so that's our domain. All right, so now let's take the derivative of this. And so, because you guys are experts with chain rule, and this isn't even chain rule, this is the constant multiple function type of rule. Or if you want to do product rule, you could. It's not necessary. But the derivative is 5 over x minus 1. Okay, and then we need to, okay, we'll talk about, well, what's the domain of f prime? Well, here, the domain of f prime would be all reals except what? 0. Okay, so all reals except 0. So therefore, okay, so we see that our domain is all reals except for 0. We have to be a little careful here because you might think, well, our only partition number would be 0. But you need to bring this together to make sure you don't miss anything. And what I mean in this, as you can see on the second line, I found the common denominator, which was x, so I just multiplied that by x over x, and we see we get 5 minus x over x. And this is very important because remember, your partition numbers are what makes the partition numbers represent what makes the function 0 or bad or discontinuous, right? Okay, and so we already know that our partition, sorry, it's kind of hard to read, partition numbers so far is 0 because that is a bad value or makes it discontinuous. But we also now, because this is not just a constant, right? And that's why I don't let that trip you up. If you ever have something where you have to bring, if you need to find a common denominator, then do that. Okay, here, and that's in everything actually. Here we couldn't bring anything together because that's natural log minus x, right? So in f we couldn't bring that together, but if you can bring it together, the expression together, then do that so you won't miss out. Or you could just set the function equal to 0 because it's not just a rational function. So either bring it together or just set f prime equal to 0. Okay, so I'm actually going to do it using, let's assume, because it's not just, if it's a rational function like in example 4, where it was just a single rational function and that was a constant there, that's why you know it's not going to be a 0. But like I said, you can set it equal to 0 just to double check. If you're unsure, just set your function equal to 0 to double check. So that's what I'm going to do here, just so you guys can see that we're going to get a 0. Okay, so I put it together, so I could have used the second one, but I just want to show you, even if you didn't see to put it together, that you can still set it equal to 0 to find your other partition point, your 0, the 0 of your function. All right, so that's adding 1 to both sides, multiplying by x to both sides, and then x equals 5. So we have 2 partition numbers, and 1 is actually a critical value because 5 is in the domain. So not only 5, because 5 is in the domain. Remember, it's in the domain of f because the domain are all positive numbers. So 5 is in the domain. So 5 is a critical number, but 0 is not. Okay, so when we do our sign chart, we have 0 and we have 5. That's a bad value. That's a 0. Remember too, since 0 is not a critical number, then that means that we're probably going to have a vertical asymptote at x equals 0 for this function. And it's a critical number for 5. Okay, and it's a 0 as well, right? So that means we're going to have that horizontal tangent there. Okay, and we actually don't even need to worry about, you don't need to worry about that section because the domain of the function is x greater than or equal to 0. But for consistency, although it's definitely not needed, but for consistency, we can keep it there. Okay, but it's not going to be needed when we think about graphing our function. Okay, but we'll keep it there for f prime. Since this is a sign chart for f prime, we'll keep that there. All right, and so let's do a test point. Let's do -1, 1, and 6. And again, I'll just keep the unsimplified function. That's fine. All right, so here we have, for 1, it's -1, 5 over -1 minus 1. So pause the video. I don't want to waste too much time doing this. Pause your video and figure out the answers to these. All right, so this is what you should have received. Again, because we know our domain of f is greater than or equal to x greater than or equal to 0, we only care about this side from that bracket to the right of the function when we're looking at our function for f prime, okay? But to answer the question, so let me put, because I know it's a lot on here. So putting everything together, our critical values or critical number is x equals 5. That's the only critical number. F is increasing on the interval 0, 5, and f is decreasing at 5, 0, 5 infinity, I'm sorry. And then, although it wasn't asked, there will be a horizontal tangent line at x equals 5, okay? Because that's a 0. All right, so I did want to show this function because this one isn't sort of a parent function. So this is the function of 5 ln of x minus x. And if you go back and look at the sign chart and see that it's making sense, we have a horizontal tangent there at 5. It's increasing from 0 to 5, decreasing from 5 to infinity. So it's representing our sign chart. Okay, so next let's talk about what's called local extrema. Okay, and we sort of talked about this a bit when we looked at or when we talked about max and min. And so let's look at these definitions. F of c is a local maximum if there exists an interval Mn containing c such that f of x is less than or equal to f of c. So if f of c is greater than or equal to f of x on some interval, then we say that we have a local maximum. And I have pictures, so we'll see pictures in a minute. F of c is a local minimum if there exists an interval containing c such that f of x is greater than or equal to f of c for all x belonging to Mn. And then a point on a graph where a local extrema occurs is called a turning point. All right. And so this, I took this from your book, and okay. And so here we see that in red we have what's known as a local minimum, right? And so you can find some interval. So it looks like some interval around here. That would be that interval Mn that's in that definition. All those values for local minimum are going to be greater than that local minimum. And so here at C4, that's also a local minimum, right? And there's going to be some small interval around there where all those values are going to be greater than or equal to f of C4. And conversely, in terms of local maximum, here at C3, we see that we're going to have, it's a local maximum at C3, okay? And if we want, and so the intervals are not unique, right? So meaning you can pick any interval where you see the value. So for a local minimum, you're just looking for an interval where all those values are going to be greater than some value you're looking at. So in this case, that's f of C2 and f of C4. And for a local maximum, you're looking for all those values on some interval where that f of C3 or f of C6 will be larger than that. Okay, so again, those intervals could be different. And we talked about this a little bit before, but now the formal term is local extrema, and it's a local max and a local min. And it's local because, as you can see on this graph here, C3 is a local max, but it's not the largest value output, right, on that graph, right? C6 is even bigger than it, right? And then if you go over here, those values are even higher. So that's why we call it local extrema, okay? Absolute extrema is something that we might get to later in the chapter where that's looking at if there's one point that's greater than every point on your function, or if there's one point that's smaller than every point of your function, then that would be an absolute extrema. All right, so now in example 6, I want to see if you can analyze this function to tell me, this function g is given here to tell me which interval is g increasing, decreasing, and what's the local max and the local min, right? So sort of working backwards from what we've been doing. So we know that the sign chart of f prime tells us where f is increasing or decreasing, right? And to find the partition numbers for the sign chart of f prime, we need to look to see where there's either a horizontal tangent or vertical asymptote or vertical tangent line. So for this, though, we just have horizontal tangent lines at 1 and at -3, right? And so we have partition numbers at -1 and I mean +1. I'm sorry. Thank you for correcting me. At 1 and -3, and then we look to see, well, what's going on these intervals. So again, we know this is from -infinity to +infinity, right? And so here we just sort of look at our graph, and again, you read a graph from left to right. So from -infinity all the way to -3, I'm going down, right? So I'm negative. That tells me I'm negative, and I'm decreasing. And then from -3 all the way to 1, I'm increasing, so it's positive. And then from 1 to infinity, I'm going back down, so I'm decreasing. So the answer to the question would be, and I'm sorry, this is G. Went into automatic mode, so this is G prime and G. So G is increasing on -3, 1, right? And these represent zeros. G is decreasing. I'm going to use DEC for abbreviation. -infinity to -3, union 1 to 3. Okay, 1 to 3. What am I doing? 1 to infinity, right? It doesn't just stop at 3. And then let's see. What about local max and local min? So let me erase all this now. And what about local max and local min? Well, you should recognize that there, and I use two different, and there we have a local max and a local min, right? And so we would say at f of -3, there. Now, because I didn't ask you for what to give me a certain interval where local max or min is, you can just give me the value. So f of -3, there is a local minima, and f of 1, there is a local maximum. All right, and we are done with this problem. I think I'm going to, let me see. Okay, so I'm gonna have you write this down, and I'm gonna stop this video and then start another one. So again, remember, this is for the rest of this week, and I think I will I still want to start 4.2 as well. So I won't finish 4.2 in the videos. We'll probably do that in class, but I'm definitely going to get through 4.1. Okay, so local extrema and critical numbers. So if f of c is a local extrema of the function f, then c is a critical number of f, okay? And so this does not mean that every critical number will produce a local extrema. So we're going to talk about when it does produce a local extrema, but what we do know is if it is a local extrema, then c has to be a critical number, okay? Not just a partition number. So we're going to stop this video here, and then I'll talk more about that in the next video.